Swayam Prabha. Digital India. Educated India.
So, we continue our discussion on color fundamentals and processing. So, in the last class, in the last lecture, I just mentioned that how colors could be represented in a two-dimensional space where only the chromatic informations, that means the informations without luminance, that could be represented as a 2D points in that XY chromaticity space. And there, as you can see here, that there is a particular range of values over which these colors are represented. So, this is the this is the particular area where all different kinds of colors are represented, and for visual experience, we have just also plotted them by the respective nearest colors. So, in the periphery, these are the colors corresponding to wavelengths. These are true colors, monochromatic representation of a color with wavelength, and there is a point within this area, and this is mostly, so you have XY chromaticity chart where you have in this direction you have the normalized X, and in this direction normalized Y. So, I have discussed how it is obtained, or it could be transformed, how the RGB representation of a color point could be transformed into a CIE XYZ space, and then from there you can get these normalized points. So, within this there is a point where actually chromatic information is almost nil, because only the luminance information, chroma is almost there, it is a white point. So, we represent those those points are in the chromatic space, those points are represented by x equal to 1 by 3 and y equal to 1 by 3, which means that all the components are equal, all the red, green, blue components are almost equal, and they provide these components. And from that point, if I move radially, then actually we are following certain color line. So, and its true color corresponds to the peripheral point denoted by certain wavelength of certain nanometer. For example, this is a yellow kind of color which is shown. So, its respective band, say in this particular case it is around, say, between 500 to 570 nanometer. So, some in between it is there, that some wavelength or some nanometer. So, this information, that means this particular radial direction encodes the hue of the color, and on the other hand, the radius itself, or the distance from the white point, it shows that how pure is the color, that means how saturated is the color. Nearer it is to periphery, it is more saturated. There is another interesting information also you can get. If I give you 3 primary points, that means 3 primary colors, using which they are additive mixing or subtractive mixing. So, their linear combinations, if I say, is producing the color of here it is basically additive mixing. So, producing the color of all other kinds of color. Now, then they define a triangle. As you know that, as you understand that only a linear combination of these primary colors are reproducible. So, outside this triangle, no color is reproducible. That means those colors, though they exist physically in the environment, but you cannot encode their informations into this form and represent them. Also, in the display device, also you cannot represent them with these primaries. But if you change these primary colors, that means this triangle, we call this triangle as gamma triangle, because it defines the range of colors that could be displayed. That is what is known as gamut. So, this is the color reproducibility part. Now, using this particular processing or this particular representation, we can think about certain color processing, which is kind of color enhancement of chromatic components, or even the de-enhancement. So, we call them as saturation and desaturation. It is more appropriate, because what we do, suppose you have a color point at P, and then as I mentioned that if you move radially, you are basically going towards more and more saturated color point. So, but there is a limit, because the outside this triangle you cannot represent any color. So, the maximum saturation point would be the intersection of this line, that means from white point to the color point. That line where it intersects, that is the maximum saturation point. So, if I would like to compute this point, it is possible, because it's just the geometry. If you know the positions of the primaries in the xy chromaticity space, then the triangle is defined. If you know the color point, white point is also defined. So, you can compute this intersection. And if you move inward, then it is desaturation. So, now how much inward you should move, that kind of depends upon your requirement. There is one interesting rule that has been proposed, that is called some sort of center of gravity rule, which means if I have the maximum saturated point and say W, here our representation is 3 dimension. So, we have this xy coordinate and also the luminance part, which is represented by this big Y, capital Y. So, then this intermediate value, it is a linear combination of this, and these weights, the rule of these weights, it is it can be computed. This weighted average can be computed in this fashion for both x and y coordinates, where you have this YW, which is a kind of as you can see that this is the destination point and the intensity, and YW is and estimated as proportional to the average illumination. So, we use certain value of K, which is some constant, and empirically you can choose. So, with these operations, you can also move the point from its saturation, maximally saturated point, to inwards following the radius. That is a desaturation. So, I will show you some effect of these operations. Say, consider this is an image which we name as Alps, because it's an image of an Alps peak, and there if I plot these color points, scatter plot in the xy chromaticity chart, and I have also shown the boundary just for the convenience. So, you can see that these points are plotted within this space itself, and there could be, roughly you can see there is a triangle, there is a triangular shape, what is indicating that this is the limit of color reproductions in this case. So, when we are doing saturated image, what we do, that by leaving aside some of the points which are near the white point, we are moving every other points towards the triangular edge. So, this is how the saturated image, and this is how the desaturated image looks like. So, after these operations, actually we have transformed it back to RGB space. Again, we replotted it in the xy chromaticity space. So, this is the desaturation operations. You can see that they are moving inwards. This is saturated and desaturated. So, some of the points are moved inwards following the center of gravity law, and even you can do some more variations. Suppose the background illumination, I have said that you multiply with K, then you have certain component of the luminance value of the processed image. So, if you use that as a negative K, then you have a softening effect of the illumination. Even if we shift the white point, then respective hue of the shifting would be also added. Suppose we are shifting towards red zone from the white zone towards red zone, then there is kind of a reddish hue it comes. So, this is different kinds of, this is towards the bluish zone, this is the effect. So, different such effects are possible with this operation. Now, this is about the representation of color in the as far as our perceptual components. We can also, but there are certain things in this XY space which is missing here. So, one of the thing is that in this case we have, so far we have discussed about our perceptual representation of color point in the XY chromaticity space. But if we observe consider any particular point, now if I certainly perturb this point around its neighborhood, our perception still remains the same. Now there is a limit, there is a boundary beyond which it will be perceptible. So this could be modeled by a ellipse around that point, elliptical neighborhood that has been observed, and these ellipses around the central point, they give you same kind of perceptual effect. So we call this kind of ellipses as macadam ellipse or just noticeable differences. So if you just go beyond the ellipse, you will notice the difference in color. But the issue is here, as you can see, that shape of this these ellipses, they are non-uniform and size is also non-uniform. So neighborhood size is increases around green, whereas it is very small around this zone. So it is about the purple zone, blue and purple zone, even in reddish zone. So this space we call, it's not very uniform. That means if we use some distance measure, for example Euclidean distance, where actually circular shapes and that too of same size around every point is more, it should have been the preferred one if we use Euclidean distance functions to denote the distance between two colors. Now that is not very convenient to do that. I mean, there is not, standardization is not there. So what we consider, there are certain color spaces where we try to take the size of this ellipse, try to bring them equal, make them in around one particular size, so more or less equal. So you cannot make them exactly equal, there will be some variations, but this variation gets smaller. Now this space is called UV space. So this is the transformation. You can see that from XYZ you can get this kind of UV transformation. Instead of normalized XY coordinate, we get U and V component in this fashion. So there, if I consider the ellipse around every point, you can see that these sizes are, though there is a variation, but this variation is smaller than what it is. So this color space is called uniform color space. There is also another color space which is rather more used for measuring the distance between two perceptually different color. Now where the Euclidean distance is most is applicable, because it's a three-dimensional representation including the intensity value, and it is the LAB space, or you can say L star B star space. So in this space or L star B star space or LAB space, but this is a transformation. You can see that now it's a nonlinear transformation. So from XYZ you have these transformations where this Xn, Yn, Zn are the reference white in XYZ space. So L star is the luminance channel, S star and B stars are the chroma channels or color channels. So the kind of variations over this three-dimensional space are shown here. So if I consider the axis of A, from negative to positive, it is from green to red, and for B, which is this axis, along this direction, it is blue to yellow, and then intensity is from black to white or luminance. So the interesting fact is that in this space, Euclidean distance is also suitable to, rather most suitable to represent the color differences. Now we will be also considering another nonlinear transformation of color space. So these are certain nonlinear transformation, as you can see that from the RGB point. So you have linear transformation to XYZ, and from XYZ again nonlinear transformations we are doing. HSV color space is also an example of another nonlinear transformations, where once again you directly encode hue and saturation. They are actually in terms of angle and radial value, which was not there earlier in the XY space or UV space. So this is one schematic representation of HSV color space, yes, with conical shape here we have shown. And if I look at every cross section, as you move radially, the hue is varying. Angularly the hue is varying, and as you move radially, it is the saturation varies. So hue is encoded as an angle from 0 to 360 degree. Saturation, the distance from the vertical axis, so it is between 0 to 1, and intensity, the height along the vertical axis, 0 to 1. See, it is HSV. Actually, this one is shown as HSI. So this transformation is for HSI. So for V also you can have this transformation. So this is the transformation from RGB to HSI value. And here in this transformation, RGB is also expressed in a normalized range from 0 to 1. One other property of HSV color space also, it is also a kind of uniform color space where equal steps you will be finding for perceiving similar color changes. I have just shown you that from RGB color space how you can get how you can transform it to an HSV color space. The reverse is also there, and since it is nonlinear, just I am showing you how the computation proceeds. Suppose you have HSV value, there is a first you have to compute this C stands for chroma, H prime and X in this using these expressions. Then from there you can get the some of the, it's basically hexagonal representation of the color wheel, if I say that angular representation of hues. So that it's an hexagonal, say points on hexagons, these are the points, and depending upon the value of H prime you choose those. Finally, the RGB values are computed in this fashion. So mathematically you can show that how it corresponds from the HSV space to the RGB space. And here also RGB is expressed in the normalized scale. Now about the color spaces, this is another interesting representation of color where there is a theory which hypothesis which is behind this kind of representation. It is called the opponent color theorem or opponent color processing. So here the theory considers that it proposes that we process signals from cones and rods in an antagonistic manner. So in the antagonistic manner we process it, which means at there are cells which takes these two inputs or 2 or 3 inputs from different cones and rods, and then there would be some of them will be exciting that cell and some of them will be inhibiting it in terms of additive mixing and subtractive mixing. Actually subtractive mix, I have already mentioned earlier that subtractive mixing is a phenomena which occurs in our visual response system, and both additive and subtractive phenomena is there. So if I consider long, medium and short range of wavelengths, so there are differences. Say this is a model which has been shown here. So as if there are three types of cone, L, M, S and rod cone. And first thing is that this is a luminance channel, which means you add both L, M, S and also you take information from rod. That is a luminance channel, which acts mostly on the, as I mentioned, low illumination cases, and these are the bright illumination cases. Whereas the channels 1, it is representing R minus G. R is basically long cone, and so L and M cone, that is giving channel 1, where it is basically green is inhibiting and red is exciting, or L is exciting and M is inhibiting. And for S cone, it is R plus G minus B. So all the 3 cones are active. So Y is basically represented as R plus G. So these representations could be in this way also. So G minus R and B minus Y, B minus R plus G. So this is another transformation. in the previous case I have shown just the opposite way. So, this is opposite opponent channel. So, this representation is also there, and there is a colors space which has modeled this interaction, and we can see that it is basically YCB CR space, but CB and CR they are translated by 128. So, to make the transformation linear, I have subtracted 128 from CB and CR. CB calls complementary blue because now you are representing in this case just the opposite of it. That means no, it is B minus R plus G, B minus Y, that is the complementary blue, and CR is complementary red. It is as you can see that this is R minus G plus B. So, that is the representation. So, in this way this color space is represented. Actual ICB CR space I mentioned that you add 128 to the CB and CR, so that now their negative values becomes positive. So, they are translated from their dynamic range to 0 to 240 values, and it is a affine transformation that we should note. So, one of the thing in the color processing that we need to consider that there is a certain effect of illumination over the recording of color signals. But the thing is that we as a human being, we adjust ourselves. So, we perceive the same color with varying illumination. So, there to certain extent we can do that with a fairly good tolerance limit. So, one example could be, say this is an image which is taken by flash, and if I take it by another kind of lamp, this image if we display, you can see that the certain hue is getting added, background hue is getting added because of the change of light source. Light source spectral power is density is affecting the recorded values, and so the display also. But as a human observer, we still perceive all these colors the same within this illumination also. So, our perception is more accommodative. Now, this is a property we call it color constancy. So, one of the objective for color processing is that how to make your representation this kind of illumination independent representation. So, as we say that RGB primaries used by different devices are usually different, and camera and light sources should be calibrated, and for multimedia applications this is more difficult to organize. So, algorithm exists for estimating the illumination color. So, this will give you some means to, because if you can get the color of the light source, then you can apply certain corrections and for making it making the color in a normalized or on its canonical environment, if I say. For example, you take an image in broad daylight, and if you take an image during sunset, so there would be recording would be different in your camera. Not only that illumination would be darker, but also the colors would look also different. But no, when if I want to normalize it, so the correction can bring those colors as if those colors are produced during the recording on the broad daylight imaging. So, let us now discuss about this particular component of estimating the light source, the light source or the light component of the light source. So, in this regard, we will be considering two types of reflection. So, one this reflected light, because that is being recorded, usually we do not directly record the light source, because that would be overexposing the either the sensors or films. So, it is the reflected light that we usually record. Now, there are two types of reflections we can see in nature. One is called diffuse, another is called specular. So, in diffuse reflection, when light is incident on the surface point, then reflected ray it reflects in all possible directions. In all possible directions, it just scatters, and the energy gets distributed equally in every directions. Of course, it is modulated by the reflection coefficient and also angle of reflection, angle of incidence. But in specular reflection, it follows the Newtonian reflection, law of reflection. So, the incident ray, the angle what it makes with the surface normal, your reflected ray will be in that along the directions which make the same normal, and as you know that all of them should lie on the single plane, all those things are there. So, point is that along a particular directions most of the energy gets traversed. Now, in the specular reflection, as you can understand, though it is modulated by the reflection coefficient, specular reflection coefficient of the surface point, still much of these spectral power density distributions what is there in incident ray, those are almost reflected by keeping the same kind of proportions reflected along the path of reflection, because most of the energy is getting reflected there. So, in specular reflection, reflection coefficient is very high, most of the energy gets reflected. So, that is why if I consider specular reflection, you will get you will get more information related to the color of the light source, whereas for diffuse reflection, you will get more information about the color of the surface. So, these two factors can guide us also developing this kind of algorithm for computing the spectral power density of light source. Now, a weighted sum of these two usually you get as a reflected light, as we understand. So, when we view a colored objects, we assume that both diffuse and specular reflections could be there in the model, and specular would be primarily responsible for providing the color of the light from their on dielectric objects on metals, and whereas diffuse, it depends on both illuminant and surface. So, our vision, as I mentioned, that effect of varying illumination can be adjusted, and that is called color constancy. So, while computing the illumination invariant representation or color constancy, we need to understand the three factors that I have already mentioned during my lecture on the fundamental topics of image processing. So, we know that there are three factors of image formation. One is that it is the optics behind it. One is that what is the spectral power density of the incident light source, what is the light source, that is incident light, and then what is the reflection coefficient, or I should say reflectance, variation of reflectance along the wavelength at a particular wavelength or along wavelengths, and then the sensor. So, what is the characteristics or proper features of the sensor sensitivity over the wavelengths. So, these three factors which are important, one is objects present in the scene, that is that reflection part, then spectral energy of light sources, and then spectral sensitivity of sensors. So this could be this could be briefly expressed, these relationships could be briefly expressed in terms of this mathematical expression. So, this is the intensity formed at a pixel x, and at that pixel we get the reflected light, it receives the reflected light through a sensor. So, at any particular wavelength lambda, say S lambda is the proportion of amount of received response, amount of received response with lambda. This is the sensitivity, filter sensitivity, sensitivity of the receptor, and then what is the reflectance along that wavelength for the object point capital X, which is whose image point is small x. So, that reflectance value and also the light source spectral power at the wavelength lambda, and you consider the whole range of lambda of the light source what is there, and if you integrate them, then you get the total energy that is accounted at particular point x. So in our model, we need to compute the spectral power distributions of the light source, but it is entangled with surface reflectance spectrum and also the spectral response of a sensor. One example could be like this once again, that these are say 3 different scenes which are captured in some illumination, and in another illumination these are captured of the same scene. So, you can see that there are certain differences with color. So, the question is that can we transfer colors from one illumination to another one? That means, if I specify the source illumination in which it is captured and also specify the destination illumination, then will it be possible to get this image from this one by knowing these 2 informations. So, this is what is computation of color constancy. First it derives an illumination representations. So, first step of this computation is that you estimate the spectral power density of light source. Now, naturally, so as I mentioned that you do not require the whole spectral profile for representing a light source, because the color mixing takes place, and because of the color mixing law, it is 3 vector representation of any reflectance, any variation pattern over the wavelength of energy distribution over the wavelength could be encoded into the 3 vector form. So, it is sufficient to estimate the colors of the light in this primary color component, and then the color correction, that is the other part, and we can use one of the corrections. So, the color correction computation is that if I know the spectral power density of the light source from the image itself, and then given my canonical conditions of illumination. So, I will be giving you a target or destination light source, again described in terms of 3 components, 3 primary components. So, can I transfer those colors under that illumination? Now, there is very simple rule which is called diagonal correction, that is applied where you consider the proportion of these primary components and use these proportions and preserving the brightness value or total brightness value of the images. So, this computation, as you can see that it just computes the red and green and blue, updated red, green, blue by this expression. So, you compute these coefficients or fractions kr, kg, kb, and also f. This is the factors you compute using the values of RGB and for a particular RGB, and you can compute this, and then finally you compute the updated red, green and blue. These are updated red, green and blue given the original red, green and blue. There are different approaches for computing the color of the light source in terms of 3 primary colors. One approach considers that the total environment is a gray. That means, if I consider the average color, it is basically it should be a gray world. So, if light source has all the spectrum, it should be gray world. But if light source is biased to certain color, so average would give me the color of the light source. That is a gray world assumption. So, just take the average of each component and by all the pixels, and then that would be your estimated color of the light source. In white world assumption, as I mentioned that specularity is a major property which shows reserves the color of the light source. So, what we here consider that wherever the maximum is there, maximum of all the components, they provide me the spectral component or spectral power factors of the light source, or I should say the 3 vector representation of the light source. So, these 2 are very simple to compute, and they are quite often used, but there are some other advanced techniques which can give you a better improved results. So, one of the technique is that you can you can attribute your illumination of the scene to one of the canonical illuminants. So, you have certain finite set of canonical illuminants. So, here the cue is that for every canonical illuminant set, you have certain color palettes which will be, which are produced which are recorded or which are produced. So, if you look at the distribution of the color points of your image, and if you try to match with one of these color distributions of the color illuminants, the closest match can give you the can give you some estimate of the color illuminant. So, it is what? Observe distribution of points in 2D chromatic space, then assign spectral power density of the nearest illuminant, which has the similar distribution in 2D chromatic space. So, there are gamut mapping approaches, and then there are color by correlation approaches. So, how these distributions are compared? How the distribution of the XY points, if I say, or chromatic points for your input image, and the respective distribution of those points which are recorded for a light source, how they are matching. So, those are the approaches. The nearest neighbor approach, here also these distributions are used. So, one of the examples here, that suppose this is your target image, and if you have so from this image, this is a gray world or color corrected using gray world strategy. This is the max world strategy, where the max is only considered for the color of the illuminant. And if I use gamut mapping, so you can see a bit better. Let us consider another case of color processing. Now, this is a bit more general than the color corrections what we discussed. So, in the color corrections, we considered a target source, and we have target light source, and we have the original light source. So, we want to transfer the color, so that as if those colors are produced by the target light source, target illumination. But color transfer, we give you example images. Instead of target light source, we give you an example images. So, it could be something like that you estimate the color of illumination of the target image and estimate the color of illumination of the source image, then you apply color correction. Now, instead of that, there are some other techniques by which you can do much better than what this kind of algorithms what I have used previously if I do it. So, I will be explain I will just explain one such technique. So, just let me show you what kind of computational task we are going to do. That suppose this is the input image, and suppose this is the example image what is given to you. You want that illumination distribution. So, your color distributions of the input image should follow the the colors produced by the illumination of this image. So, this is the source, this is target illumination, and it is the color transferred image, which is much clearer than what you have seen here. So, how we have computed? There is one algorithm. I will just simply describe this algorithm without going much into details of its principle, but it is it could be understood very easily that what we are doing, we are separating out luminance part and chrominance part, and then processing the chrominance part, and in the separated domain, we are considering the distributions of this every component, and based on those distributions, we are doing scaling of values. So, let me explain with this operation. Say, first we convert it into an LMS cone space. It's an as you can see, it's a linear operations, and this LMS stands for, once again, long, medium, and small wavelengths, wave components related long, medium, and small. And then we use the logarithmic rule, because our perceptual ranges or perceptual levels, they follow this kind of logarithmic operations. And then from LMS, there is a opponent color space. It's a bit variant. We call it L alpha beta. You can see that this is the interaction. See, first component is addition of all these three, and then this component is basically L plus M minus 2S, and this is L minus M. So again, it is the opponent color space with this theorem, and these components are once again scaled by these factors. So this L alpha beta, in this space, we are performing those modifications. We are performing those transformation. So from the source images, we find out compute the mean, and it is mean independent. We shift the representations, the values around that mean. For the processing, what we will be doing, we will be scaling these values. So we take the standard deviations of the target image and standard deviation of the source image of all these components, L alpha beta components, and their proportion will be the scale factor. So we use that scale factor. Finally, we translate it with the mean of the target image of L alpha beta component, and then again perform the inverse transformation. That means from here you first get LMS, then from there instead of log you perform exponentiation, and after that you get back the RGB to inverse transformation, because finally you have to get in RGB. So this is how that image is produced. I will give you the other example. Suppose your target illumination is this one instead of the other one, and this is your source image. That means these colors are to be transformed as if those objects are illuminated by the illumination of this target image. So if I perform this computation following the same algorithm, you can see that this artificial reddishness is now over encompassing the whole scene. So this is another example of color processing where you can transfer the images. The last operation which I am going to discuss here, that is on a demosaicing operation or interpolation operations. The motivation here is that whatever images, mostly images what we are capturing today with this low cost cameras, even including the cameras in your mobile phone, it has only one sensor. It does not have three sensors for each red, green, blue components, as we have understood earlier. What it does, instead of, it has at every place there is only one sensor, not the three sensors, and it senses only one of the spectral band. So this sensing over the spectral bands, it is basically interlinked. So it is interlinked, and suppose this place it senses only green, this place the sensor has only the sensitive to red zone, and this alternates in the first row. In the next row, this place it is say blue, it senses the blue, records the blue spectral zone. The next one is green, and it alternates, and this pattern alternates for row wise also periodically. Now this is one kind of pattern. Now this pattern could be a different in the template could be different. So this pattern is very popular. This is called Bayer's pattern, and mostly most of the research community, they use this pattern for developing algorithms. So the computation here is that if I give you an image in this form, we call it color filter array. So that it contains the color information, but it contains in an interlinked manner. So can you reconstruct the full color image? So that is the computation. So this is called color demosaicing. Now there are two observations which are vital and which helps in designing efficient algorithms. One is that there is a correlation, there is a high correlation between these three primary channels. So if we can estimate one channel, probably your predictions for the other channel would be guided by that correlated factors, right? So that's why you may require less number of information theoretic wise that there is a redundancy, so your representation does not require that much of it. But no, this can be used. And the other one is that we have considered that our visual system is more sensitive to the green channel and the luminance channel particularly. Our luminance sensitivity, we have seen chroma sensitivity. In chroma sensitivity, blue, red, they are very sensitive, the differences. But in green channel, the luminance sensitivity is high in that green wavelength zone. And that's why we sample the green twice the rate of red and blue. If we see the Bayer's pattern, that is the So these two observations are important. So and accordingly those patterns are designed. So some techniques I will discuss. One is very simple bilinear interpolation techniques, where the idea here is that, or any interpolation technique, there are few cases which you have to identify depending upon its neighborhood and depending upon your problem state at that point. Suppose here the red pixel is available by this design of mask, which means I have to estimate the green and blue part. So red is available. So for missing blue, I can use these diagonal neighbors, and for missing green, I can use this 4 neighbors, that vertical and horizontal neighbors. Here, if I consider the red estimation, I have only 2 horizontal neighbors, and here if I want to estimate blue, I have 2 vertical neighbors. So there are few such patterns which can be easily coded. So depending upon position. So the position here, one scheme we can say like this. Say every row there is a alternate green and non-green position. So I will say this is a green position and these are non-green positions. Similarly, every row is, all the rows alternatively characterized by red and blue, red and blue encoding, which means every column either green and non-green, and every row either red or blue. So with these two attributes, that means given a starting positions, say it is green and also it is red row and green positions, I know that next position would be red in this horizontal neighbor, the vertical neighbor in the downwards it would be blue, or even upwards also it will be blue, and the diagonal would be green. So all these patterns are, these patterns can be easily encoded with this location, with this kind of zones. So while interpolations, we consider few cases like this. That means the points where green is missing. So every point where green is missing, we know there are 4 green neighbors, they are always available. So you can take, for bilinear interpolations, I will take simply average of them. So we can interpolate the green pixels like this. Whereas for red and blue, you can consider a positions like R7, I am just showing here. That means 7th, the cell number 7 here. In that location, when you are computing red, you have to take 2 vertical neighbor, and the blue you have to take horizontal neighbor. And this is the 8th location. 8 means this one. When you are computing red, you have to take the diagonal neighbor, which means when it is a blue row and non-green cell, blue row and non-green cell, then for red you have to take diagonal components for interpolations. Since there are 4 values, divided it by 4. When it is blue row and green cell, then you have to take 2 vertical samples for interpolating red, and vice versa. It goes vice versa for blue and. So this is a very simple scheme. This is called bilinear interpolation. This could be improved by considering cross-channel correlations. So here we can first interpolate the green pixels and then use these values to compute the hues, red and average hues. So instead of averaging over the pixel values, we average over the hues. So consider this place where you are computing blue. So you take the blue hues. So hue is defined by the respective component divided by the green. So ratio between blue and green is blue hue, ratio between red and green is red hue. So these are the two things. So average of blue hues, and then again you multiply with the respective green value, then that would give you blue. Similarly, you can get the value of B13. So B13 is here. Here you can see that the same thing you are doing. Or even B12, here I think diagonal thing will be coming, right? So you have the 4 cases. In the same way you do for the red pixels also. Another technique, the previous technique is called average of red and blue hues, by averaging red and blue hues. That is ARBH, that's the acronym we used. Whereas this technique is I should say it is one of the best techniques, or one of the good best performing techniques, because it performs the second order correction over interpolation. It takes that second order derivatives, it estimates from its cross channel information. So what it also considers, that it observes the gradient direction of gradient. So that, as you understand, that along edges, if you perform interpolation along edges, then edge structure remains same. But if you perform across edges, then edge gets blurred. So the purpose here is that when you interpolate, we should interpolate in the direction of smaller gradients. So for example, we have the options of computing, taking average in all 4 directions. For example, for green, at this point we want to get green pixels. Instead of taking average of all 4, I will compute the gradient along these directions and along these directions. And then whichever is less, I will use it for that. And whichever is less, I will use it for that, right? But for estimating this gradient also, I have taken also a second order, corrections. I have more second order derivative factor, which is computed from the blue values. And this is how the second order derivative factors are there, as you can see. So we consider sum of these two, and whichever is less, we take it. Okay. So finally, this correction we take. This correction we take for interpolations, as you know that if I use the Taylor series expansion, now you can have the first order derivative and then the second order derivative, you can put them into your considerations. So this is how these expressions are derived. Similarly, for red and blue pixels also, you perform similar operations, because in red and blue sometimes you get diagonal directions instead of vertical and horizontal directions. Say at this condition, at this point, you are estimating red, so you have these diagonal values, and use them for your computation of derivative, and then you perform these corrections. So this algorithm also is using this fact. And as I mentioned, these are the Laplacian values, and this is some example that how different color, this ARBH is missing, but this is original image. This is bilinear interpolation. This is LCEC, or Laplacian corrected edge correlation technique. But two major problems are there in this reconstruction. One is that, as you understand, that edges are blurred, and the other one is the false color, appearance of false color. So this is an example of appearance of false color. See, this is an original image, and I have made the color filter array out of it. So I have taken simulated and color filter array by retaining only one spectral band at every location in that following certain pattern. Then apply an color interpolation algorithm, then you reconstruct. So you can see in the fences where there are high frequency components are very high, significant, this color imbalance is causing this kind of false color, appearance of false colors. So one of the technique by which we can suppress this false color is that perform median filtering. So false color is something like salt and pepper noise. So apply median filter in the chromatic components only. So convert RGB to IEV space, apply median filter there, then filtered again you reconstruct back, you project the true samples also there. So that would give you, the effect with this could be reduced effect it will give. So even if you plot them, you will find that impulsive. So this is kind of original one, and if I do the median filtering, then you can see some of this impulsive noise is getting reduced. So with this, let me conclude this particular topic on color processing. One thing is that it is a very important information for interpreting images and videos, and color is captured in RGB color space. So it is not suitable for direct interpretation of color components. That is the problem with RGB space. But we can use calibrated color representation in the chromaticity chart representations according to tri-stimulus model of color representation. And there we have seen that how gamma triangles are interpreted for providing you set of reproducible colors. Then there are various other color spaces which are used for processing, and in digital cameras particularly, color images are mostly captured using a color filter array, which and there are few more problems on color processing also have discussed, such as enhancement through saturation, desaturation, computation of color constancy, then color transfer. Of course, the last one, what we discuss is color interpolations. So with this, let me stop. Thank you very much for your listening.